In order to understand the FEMs more deeply in this section, we consider approximating the solution to a more general boundary value problems in this form. From the earlier one, we have extra terms, here first term, and also the function value term. And for now, the equation is defined over the interval from 0 to 1. At the left edge point, now a function value, non-zero value is given. At the right edge point, now the derivative value is given. So it's a little more general. Such a boundary condition is called the Dirichlet boundary condition, and sometimes it's called essential boundary condition, while this Neumann boundary condition is called a natural boundary condition. To solve this problem, again, we should start with a variational formulation. To deal with this one, non-homogeneous boundary condition, we need a little bit of complication. However, in fact, it's not really real complication. Let's see the variational formulation. We define two linear spaces. In the beginning, now v is here continuous function, and its derivative is piecewise continuous over the interval. That is v, and among these functions, we collect the functions having value 0 at left edge point, so that this is v, this is v0. So this is a simple restriction, and that's 0 over there. Now, if we try to use the integration by parts, then first multiply test function, but the test function will be chosen from v0, so that left edge point, the value is 0. V is chosen from here, so the v at 0 must be 0. Now, after multiplication, we apply the integration by parts, and we have that. And at x equals 0, this value is 0. Now, only at x1, we have this quantity, and we have this term. So that once we apply everywhere the multiplication by v and integration, then, and also using this integration by part, we can reach at this equation. This term is now moved to the other side. Okay, we reach at this one. This is the weak form of this differential equation. So it is a strong form, and this is weak form. Now, we can define the bilinear functional for this left-hand side, that is BUV. For the right side, we say there's LV. Then this can be written in this simple form. And now we define the variational problem corresponding to the given differential problem. Now we try to find U from V. Okay, let's go to the linear space, so that now we have to find the solution inside of V, not V0, V, such that now this one, the test function, is chosen from V0, because at the left edge point, the value is known, so that it doesn't, okay, at the left edge point, it doesn't have to be unknown, so that in fact this test function is to get the linear system, and so that we can choose only test functions from the subspace or subspace of V0. So it is organized in this way. So it's a little bit more complicated. However, practically no unknown is increased because we use the known value later on in FEM, the integration. So when we try to get the algebraic system, there's no unknown involved explicitly for the left edge point, because we try to choose the test functions, the weight from only this space. Okay. The differential problem is equivalent to the variational problem when the second derivative exists. Exactly the same way you can prove that as for the homogeneous boundary conditions. Now, once we know the differential problem and variational problems are the same, and also maybe you may consider minimization problem so that they all are equivalent, and then they'll admit unique solution with when some conditions are satisfied. We assume that's done. Now, from this variational problem, we'll try to introduce finite element method. Let's focus on linear case and also Galerkin. Galerkin method is a weighted residual approach. Okay, let's go the finite element design step by step. Again, we have 4 steps. In the beginning, partitioning. So given interval must be partitioned. So each subinterval is ij, and length of hj, the maximum of hj is h, as earlier we did. Now, for subspaces, we have 2 linear spaces, so that we have to have now 2 subspaces, but it's not really quite independent of each other, only small change. Now, that VH is the functions in V and such that locally linear. On each subinterval, the function is linear because we are dealing with linear Galerkin right now, linear FEM, so it must be linear. And now, as a subspace of a V0, we are considering, in fact, the almost same, only the additional condition is that at the left edge point, the function value is 0. Okay. So we can, along with this one, we can make a basis function for VH. So phi j is collection basis function from 0 to m for every point. Now, the basis functions are defined. Along with these basis functions, we can now formulate our numerical solution. That is, from 0 to m, linear combination of the basis function. Of course, left edge one, leftmost one, and phi j and phi 0 must be alpha. This is the Dirichlet assigned value. And so that practically the number of unknown for this equation is m rather than m plus 1. Already one value is known. In this way, we formulate our finite element solution. And when we are trying to use a variational principle from a Galerkin method, then we try to choose the weight functions from the basis functions. Now, the basis functions are chosen from this smaller subspace. That is, at the left edge point, the value is 0. we don't need to get anything more complicated than this one, because already at the left edge point, the value is known here. There is 0. In fact, this is x0. Now already the height is known. There's alpha. This value is known. So we don't have to introduce any further complication. And now we try to choose the m test functions, weights, and to for this equation, and so that we have m equations and here m unknowns, so we can get a linear system. Okay, here for each B and L, we have detail here. Now, okay, that is Aij. So here that is a Ji, J prime, phi J prime, phi I prime. Now that must be now phi J prime. J is coming from the linear combination of the basis functions. Now I, phi I, came from the weight, the test function. So you have to be careful. And in many cases, people are making mistake by changing this one, because over there, even though you change ij, it doesn't matter for this one. But for this one, if you change ij, then you have a big problem. Okay, it's not working. Now L phi I, okay, and after getting this one, you can get right side bi, and after getting these values through integration, you may use again the trapezoid rule, and you can get these quantities and form an algebraic system. Once the algebraic system is solved, then you got the unknowns and your job done. Let's see one example. We solved this problem along with finite difference method, and let's try to solve this problem using the linear Galerkin FEM. And left edge point, the value is 0, and right edge point, the slope is -2. And for this problem, we'll try to solve the problem twice, one with h1/8, 1/5, and the other one with h equals 1/10. The exact solution for this problem is this one. Now, here you can see the solutions from linear Galerkin FEM and solutions from the earlier and from finite difference method. Let's try to see error, compare errors. Okay, for example, now when h is 1/5, the errors are given in this way through the points, and now through the points we have this error. Okay, as you can see here, the error from the linear Galerkin FEM is smaller. And also for the case h is 1/10, the error is also smaller than those here in FEM solution. So for this example, the linear Galerkin method is better than the finite difference method. But in most cases, they are quite similar. Once you choose the uniform mesh, then the Galerkin FEM will produce almost the same solution as the finite difference method. Okay, now you may again, one more time, listen to the FEM song. It'll give you better understanding. Okay, and I'll include the link in the below. So try to listen to music and understand the FEM better. Okay, thank you. This is end of the chapter.